Here is the model for a two-factor random effect experiment. Notice that both main effects and the interaction are random, so they have a distribution. We will check the assumptions in the same manner we did for the fixed case. We need to create the EMS table so that we can determine the correct test statistic. Here are the test statistics for this model. Notice that the mean square for the interaction is used to test the main effects. This is different from the fixed case where we test everything with the MSE. How did we come up with these ratios? We find the term that yields the same EMS as the effect in question given that the null is true. So for effect A, we assume that the variance component is 0 under the null. This means that it has the same EMS as the interaction, so we build our test statistic using the interaction mean square. Now we need to figure out a way to get the EMSs. We have a set of rules that we use to create the EMS tables. We need to write the errors in terms of the nesting structure within it. Let K be the subscript that represents the replicate number and I, J, represent the specific levels of the two factors. The parentheses mean that the observations are nested under the treatment combinations. This means that each observation comes from only one treatment combination. Now list the effects with their subscripts. Let's classify the subscripts. Notice that the first row and column identify which subscript belongs with which effect. The term live means that the subscript is represented in the effect. The term absent means that it is not represented. The term dead means that it is represented, but something is nested under it. Now let's determine what the contribution each effect gives to the EMS. For the random effect, it is the variance component. For a fixed effect, it is the sum of the squared effects over the number of levels minus 1. Let's create the skeleton of the EMS table. Take the first 3 rows and identify the type of factor, the number of levels, and the subscript that it represents, which is the number of levels. The first column represents the effects themselves. First, we put 1s in columns with dead subscripts. Now put 0s in columns for fixed factors that have live subscripts, and 1s in columns for random factors that have live subscripts. Now write in the number of levels for the absent subscripts. For example, if there is an absent subscript in the column with subscript A at the top, then we put an A in the spot where the subscript is absent. Now to get the EMS for an effect, we need to cover the columns that include its live subscripts, and cover the rows that include any absent subscripts. Starting from the bottom, we need to multiply through the rows that are left by their contributions to the EMS and add them up. So for effect A, we need to cover the first column since it has a live subscript for A. Now we need to cover the row that corresponds to effect B since it has the only absent subscript in this case. Now multiply through then add. This means that 1 sigma square plus 1n sigma square AB plus bn sigma square A. We do the same thing for effect B. You should be able to get the EMS that you see on the slide. For the interaction, notice that both columns are covered. This should not be surprising because both subscripts were live. For the rows, notice that both effects A and B have an absent subscript for the other effect in them, which means that we need to cover both rows. Now convince yourself that the EMS on the slide is correct. Notice here that the last column is the only one with a live subscript for K, so we cover that column. We need to cover all 3 effect rows, since each one has an absent subscript in the K column. So here all that is left is the ones in the error row, which means that the EMS for error will be sigma square. This will always be the case. Here are the expected mean squares. Now how do we get the variance components? Well, we get them by substituting the correct mean square into the equation for the EMS and solving for the specific variance component. Now we can substitute the variance components that we found into the other equations to find all of the components. I would do this by starting off with the error term and working my way from the bottom up the table. Here is an example with 2 random factors. You should be aware that this is an example of a measurement system study. We are trying to determine if the majority of the variation is caused by the difference parts, operators, or by the measurement gauge itself. Sometimes this is referred to as a gauge R&R. Here are the experimental results. Notice that this is balanced. In other words, each of 2 operator is measuring each of 10 part 3 times. The results show that the only variance component that is different from 0 is the one for parts. Now let's find the variance components. Based on the estimates, 2 of the variance components are negative. We know that this can't happen. Recall that they are negative because of the method of moments estimation is inefficient. Also recall that for negative variance components, we assign them a value of 0. Notice here that I did not reduce our model. Think about why I decided not to do this. So the percent contribution from the parts is 54%. This means that the percent contributions from measurement error is 46%. We consider the measurement system not adequate because the amount of variation due to your gauge is too high. We would like the variation due to parts to be 80 or 90%. Some models will contain both fixed and random effects. We will analyze the fixed effect using the technique for fixed effects and the random ones using the technique for random effects. We still need to create the EMS so that we can determine the correct test statistics. Since an interaction that has a random effect in it actually has a random component, we will consider it a random effect. Here is the model for a two-factor mixed effect model. Notice that a Greek letter is used to represent the fixed effect. Also, the interaction has a distribution. Let's find the EMSs for this situation. Here are the speaker notes for the current slide. Now that we've established how to calculate expected mean squares for mixed models using the rules we set up earlier, let's consider a specific example to illustrate this concept. We have an experiment with two factors, one fixed factor with A levels and one random factor with B levels. There are also n replicates in each combination of these factors. This setup is crucial for determining the expected mean squares, as we'll see shortly. To create the expected mean square, EMS, for this mixed model experiment, we need to consider several components: the fixed effects, random effects, and residual errors. The EMS will be a weighted average of these components, reflecting their respective variances. Let's denote the EMS for the fixed effect as A, the EMS for the random effect as B, and the EMS for the interaction between the fixed and random effects as AB. We also have the EMS for the residual errors, denoted as E. The EMS is a critical component in determining the F ratios for each effect. To calculate these F ratios, we need to compare the observed mean square, MS, with the expected mean square, EMS. The ratio of MS to EMS gives us the F statistic, which helps us determine whether an effect is statistically significant. In our example, we have two types of effects, fixed and random. We'll use the rules for mixed models to calculate the EMS for each type of effect. This will enable us to compare the observed mean squares with their expected values and make informed decisions about the significance of each effect. Now that we've set up our example, let's proceed to the next step in calculating the EMS contribution for each factor. Notice here that we have altered the contribution from the first effect to represent it as a fixed factor. Notice here that we now give the fixed effect cell where the subscript is live as 0 since it is fixed. Also, we continue to use ones in the interaction row since we consider it random. Notice here that we now give the fixed effect cell where the subscript is live as 0 since it is fixed. Also, we continue to use ones in the interaction row since we consider it random. Now that we've explored the effect of a random factor on our data, let's consider how to quantify its impact using expected mean squares. To compute F ratios, which will allow us to make inferences about our model, we need to understand what these values represent. The expected mean square for the error term, denoted by EMS_E, is a crucial component of this process. It represents the average squared difference between observed and predicted values when there's no real effect present. In other words, it's an estimate of the variability in our data that's due to random chance rather than any systematic differences. This value is often denoted by sigma squared or sigma superscript 2, and it plays a central role in ANOVA calculations. Now, let's examine how we can compute expected mean squares for other terms, such as the factor itself. We'll see how these values are used to construct F ratios, which will enable us to make informed decisions about our model. To do this, we need to consider the relationship between the factor and the response variable. This involves understanding the variance components that contribute to the overall variability in our data. By breaking down the total sum of squares into its constituent parts, we can gain insight into the relative importance of different factors. As we move forward, keep in mind that these calculations are based on certain assumptions about our data and model. We'll discuss these assumptions and how they impact our results in subsequent lectures. Now, let's proceed to the next slide, where we'll explore the process of computing F-ratios in more detail. To compute F-ratios, we need to consider the expected mean squares, which we've already discussed on the previous slide. The expected mean square for the treatment effect is denoted as E(ms)(a), and it's calculated by taking the sum of the variance components associated with each factor. Now, let's recall that the F-ratio is essentially a ratio of two variances. We have the mean square between groups, which represents the variation due to the treatment effect, and we have the mean square within groups, which accounts for the residual or error variation. To compute the F-ratio, we'll use the formula F equals E(ms)(a)/E(ms)(e). Here, E(ms)(a) is the expected mean square for the treatment effect, and E(ms)(e) is the expected mean square for the error term. The F-ratio can be interpreted as a measure of how much variation in the response variable is attributable to the treatment effect relative to the residual or error variation. A large F-ratio indicates that the treatment effect is statistically significant, suggesting that there's a real difference between the groups being compared. However, we must also consider the degrees of freedom associated with each term. The numerator and denominator of the F-ratio formula both involve different degrees of freedom. We'll need to use these values to determine the critical region for our hypothesis test. In practice, computing F-ratios can be a bit tedious, but it's essential for making informed decisions about your data. By understanding how to calculate F-ratios and interpreting their results, you'll be better equipped to identify statistically significant effects in your experiments or studies. As we move on to the next slide, we'll explore variance components in more detail, examining how they contribute to the overall variation in the response variable. This will help us refine our understanding of the F-ratio and its role in hypothesis testing. Now that we've calculated the F-ratios, let's move on to understanding variance components. This is a crucial concept in mixed models, as it allows us to quantify the variability within each level of our data. As you recall from earlier lectures, variance components represent the amount of variation attributed to each random effect in our model. In other words, they measure the extent to which individual observations deviate from their group means. The formula for calculating variance components is based on the residual mean square, MSE, and the degrees of freedom associated with each level of the data. Specifically, we use the following equation. var alpha equals MSE/df, where var alpha represents the variance component for a particular random effect, MSE is the residual mean square, and df is the corresponding degrees of freedom. To illustrate this concept, let's consider an example from our previous discussion on F-ratios. Suppose we have a model with two levels, subjects and treatments. We want to estimate the variance components for both subjects and treatments. Using the data provided in the table, we can calculate the MSE as 36. Now, we need to determine the degrees of freedom associated with each level. For subjects, this would be N1, where N is the number of observations per subject. Similarly, for treatments, it would be N1*K, where K is the number of treatment levels. Once we have these values, we can plug them into our equation to obtain the variance components. This will give us a better understanding of how much variation exists within each level of our data. Now that we've covered variance components, let's move on to the next topic, confidence intervals for mixed models. Now that we've discussed variance components, let's move on to constructing confidence intervals for mixed models. This is an essential concept in statistical analysis, as it allows us to quantify our uncertainty about the fixed effects. To create a confidence interval for a fixed effect, we need to replace the traditional mean squared error with a more appropriate estimate that takes into account the random effects. This is because the fixed effects are now influenced by both the systematic and random components of variation. In essence, we're shifting from a purely parametric approach to one that acknowledges the role of variance components in shaping our estimates. This requires us to reevaluate how we interpret the results of our analysis. Let's consider an example to illustrate this concept. Suppose we're conducting an experiment with two factors, and we want to estimate the main effect of one of the variables while accounting for the random effects. How would we construct a confidence interval in this scenario? To do so, we need to understand that the fixed effect is now influenced by both the systematic and random components of variation. This means that our estimate will be subject to some degree of uncertainty, which we can quantify using a confidence interval. The key takeaway here is that constructing confidence intervals for mixed models requires us to consider the interplay between fixed and random effects. By doing so, we can obtain more accurate estimates and make more informed decisions based on our results. Now, let's move on to discussing K-factor experiments with mixed and random effects. As we'll see, many of the concepts we've discussed so far can be generalized to these more complex scenarios. Let's move on to K-factor experiments with mixed and random effects. As we discussed earlier in the context of two-factor cases, the principles can be generalized to accommodate any number of factors. In a K-factor experiment, we have multiple fixed effects, which are typically denoted by uppercase letters such as a, B, C, and so on. These factors are assumed to have main effects, as well as interactions between each other. The mixed model framework allows us to incorporate both fixed and random effects into our analysis. Random effects are typically denoted by lowercase letters, such as A or B, and represent variation that is not of primary interest but still needs to be accounted for in the model. To construct a confidence interval for the difference between two levels of a fixed effect in this context, we need to replace the mean square error with an estimate of the variance associated with the fixed effects. This is because the fixed effects are assumed to have a non-zero value, whereas the random effects are assumed to be zero. The K-factor experiment can be viewed as an extension of the two-factor case, where additional factors are introduced and their interactions with each other and the existing factors need to be considered. The mixed model framework provides a flexible way to handle these complex designs by accounting for both fixed and random effects. In the context of K-factor experiments, it's essential to consider the potential interactions between factors and how they impact the overall analysis. This includes examining the main effects of each factor, as well as their interactions with other factors. The concept of a K-factor experiment can be applied in various fields, including agriculture, engineering, and social sciences, where researchers often need to investigate multiple variables simultaneously. To illustrate this further, let's consider an example of a three-factor experiment with two levels for each factor. We would need to construct a model that accounts for the main effects and interactions between these factors, as well as any random variation present in the data. In the next slide, we'll discuss the concept of random blocking factors and how they can be incorporated into our analysis when there is a block by treatment interaction. When dealing with K-factor experiments, we can generalize our previous results to accommodate mixed and random effects. This is a crucial concept in statistical analysis, as it allows us to account for variability in our data that may not be of primary interest. Now, let's consider the scenario where we have a block variable that is random. In such cases, we're not interested in the individual block effect itself, but rather any potential interaction between the block and treatment variables. This is where the concept of blocking comes into play. Blocking is a technique used to reduce variability in experimental data by dividing it into homogeneous subgroups or blocks. By doing so, we can isolate the effects of interest and increase the precision of our estimates. However, when dealing with random blocking factors, things become more complex. We need to consider whether there's an interaction between the block and treatment variables. In other words, is the effect of the treatment variable dependent on the specific block? If so, we have a block by treatment interaction which can significantly impact our conclusions. This is where statistical analysis comes in. We need to determine if this interaction is statistically significant or not. To do this, we'll be using ANOVA terms and regression equations to model the relationships between our variables. We'll also be conducting hypothesis tests to determine whether any of these effects are statistically significant at a 5% significance level. This will allow us to draw conclusions about the experiment and make informed decisions based on our findings. In the next slide, we'll be looking at an example of a temperature experiment that illustrates some of these concepts in action. We'll be analyzing data from this experiment using the techniques we've discussed so far, and drawing conclusions based on our results. As we move forward in our analysis of this temperature experiment, let's first consider the experimental design that was employed. We have 3 digital thermometers being compared across 2 different sites, the mouth and under the arm. For subjects were selected at random to participate in this study, and each treatment combination was measured once for each subject. This design allows us to examine not only the main effects of the thermometers and the sites, but also potential interactions between these factors. Specifically, we're interested in investigating whether there's a subject-by-site interaction, as the experimenters hypothesized that subjects may vary in their body heat. To analyze this data, we can use a two-way ANOVA to examine the main effects of thermometer and site, as well as any potential interactions between these factors. The F statistic will allow us to determine whether there's a significant difference between the means of each treatment combination. In particular, let's focus on the interaction term between subject and site. This is where we're looking for evidence of a subject-by-site interaction, which could indicate that different subjects respond differently to the 2 sites. If this interaction is statistically significant, it would suggest that we need to control for this effect in our analysis. Now, as we move forward with the analysis, keep in mind that the F statistic will provide us with a p-value, which will tell us whether the observed differences between treatment combinations are due to chance or if they're statistically significant. If the p-value is less than 0.05, we'll reject the null hypothesis and conclude that there's a statistically significant difference. Let's proceed with calculating the F statistic for this interaction term and see what conclusions we can draw from the results. Here are the speaker notes for the current slide. As we proceed to analyze the experimental results from our temperature experiment, let's first examine the data presented in this table. We have 4 subjects, each measured at 2 different sites in the mouth and under the arm, using 3 different digital thermometers. The response variable is time, recorded in seconds. Note that the data is arranged by treatment combination, with each row representing a unique combination of subject, site, and thermometer. This arrangement allows us to easily identify patterns or trends in the data. Looking at the values for each treatment combination, we can see that there is considerable variation in the times recorded. For example, subject 11 measured in the mouth using thermometer 1 took approximately 62 seconds, while subject 22 measured under the arm using the same thermometer took over 310 seconds. As we analyze this data further, it's essential to consider the potential impact of subject variability on our results. Since subjects may differ in their body heat, there could be a significant interaction between subject and site. This is an important consideration when interpreting our findings. In the next slide, we'll explore how to use SAS code to perform an analysis of variance, ANOVA, on this data, examining the main effects and interactions that influence the time required for each thermometer to register body temperature at both sites. Let's take a closer look at the data distribution. What do you notice about the spread of values within each treatment combination? Are there any outliers or unusual patterns that catch your attention? Now, let's proceed with analyzing this data using SAS code, which we'll examine in the next slide. Now that we've examined the experimental results, let's take a closer look at the SAS code used to perform the ANOVA analysis. This code is crucial in understanding how the statistical software interprets and analyzes our data. The proc-glm statement initiates the general linear model procedure in SAS, which allows us to specify the model we want to fit to our data. In this case, we're modeling the response variable time as a function of several predictor variables: subject, therm, site, and their interactions. Notice that we've specified the class statement to identify the categorical variables in our dataset. This is essential for SAS to recognize these variables and perform the necessary statistical analyses. The model statement defines the linear model we want to fit. Here, we're including main effects for each predictor variable, as well as interaction terms between therm and site and subject and site. The inclusion of these interaction terms allows us to examine how the relationships between our predictor variables are influenced by other factors in the dataset. Now, let's take a closer look at the random statement. This is where we specify the random effects in our model. In this case, we're including both subject and the interaction between subject and site as random effects. The test option allows us to perform hypothesis tests for each of these effects, using the appropriate error terms determined by the expected mean squares. The contrast statement enables us to define custom contrasts between specific levels of our predictor variables. Here, we've defined a contrast called Site 1, Site 2 that compares Site 1 and Site 2. This allows us to examine how the relationships between our predictor variables differ between these two sites. Now that we've examined this SAS code in detail, let's move on to the next slide, where we'll explore the variances of our data using the proc-varcomp procedure. As we transition from ANOVA to variance components, it's essential to understand that the test function in SAS performs hypothesis tests for each effect specified in the model, utilizing appropriate error terms determined by the expected mean squares. In other words, when we run a test using proc-GLM, SAS is evaluating whether the observed effects are statistically significant. This involves comparing the observed variance components to their expected values under the null hypothesis of no effect. Now, let's examine the code for proc-varcomp, which estimates variance components in the model. Here, we're specifying that the method should be type 1, which is a common approach for estimating variance components. The class statement defines the classification variables, including therm, site, and subj. These variables will be used to estimate the variance components associated with each effect. In the model statement, we're specifying that time is the response variable, and we're including all main effects and interactions as fixed effects. The /fixed equals 3 option indicates that we want to estimate 3 variance components, 1 for each of the main effects. By running this code, SAS will provide us with estimates of the variance components associated with each effect in the model. This information can be used to inform our understanding of the data and make more informed decisions about future experiments. Let's move on to the next topic, which is split plot designs and nested designs. These are important concepts in experimental design, and we'll explore them further in the next section.